In this work, we present a probabilistic contact state estimation framework for legged robots. This approach is based solely on inertial information. Legged robot locomotion can be regarded as a sequence of contacts between the robot's feet and the ground. This ability to discretize space facilitates legged robots to climb stairs and traverse rough terrains. In addition, estimating the quality of contact that each foot experiences with the ground is essential for base state estimation and full body control. The most mainstream approach in order to classify the contact state is to simply threshold the vertical ground reaction force. When the force measurement is greater than the empirical threshold in the top right graph, the contact is classified as stable. When the contact is firm, this approach works in practice, however, it performs poorly when walking on a slippery or soft terrain. In this work, we aim at estimating the probability of stable contact, solely by employing an IMU mounted on the robot's foot. Accordingly, we estimate the probability density function of the proposed measurement model by using kernel density estimation for each axis of the IMU independently. The estimated PDF for 100 acceleration measurements is illustrated. As can be observed, a few outliers do not affect the overall distribution considerably, and thus, making the proposed method outlier robust. To extract the per-axis probability of stable contact, we integrate each one of the 6 estimated PDFs over a symmetrical interval which is set experimentally. To evaluate the proposed method, we employed an Atlas simulated humanoid, a TALOS and a GO1 quadrupedal robot, on various terrains. In the first experiment, we commanded Atlas to walk on a normal surface in order to validate our approach. Next, we compared our method with the ground truth. Interestingly, the predictions follow the expected pattern. In exactly the same way, we deployed a real TALOS robot and observed a similar response pattern. Next, we deployed Atlas to walk on an extremely slippery surface and we compared our predictions with a state-of-the-art approach for quality of contact estimation, namely fuzzy C-means clustering. In the graph, we illustrate our predictions compared with the ground truth and the FCM approach. Although the FCM approach utilizes not only inertia information but also force and torque measurements, it produces inferior results compared to the proposed method. In the second experiment, we've explored a soft terrain scenario to showcase that our approach does not rely on the vertical GRF measurements to classify the contact. Since the vertical GRF values are lower compared to walking on a normal surface, the simple threshold approach would be ineffective in such cases. Next, we commanded the robot to walk on a grease-slippery surface. Notice that the vertical GRF pattern does not indicate that slippage occurs. Finally, we employed our approach in real time with an IMU mounted on the green foot. We have coded the robot to stop when unstable contact is detected. Similarly, we programmed the robot to find balance, without moving forward when it is unstable. Without slip detection, the robot is hopeless.